In the autumn of 2017, a small team of researchers stood on a mud bank in central California and watched a salt marsh quietly fall to pieces in front of them. There was no storm that day, no flood. The water was flat and gray and completely ordinary. And then a slab of living marsh, about the size of a kitchen table, simply detached itself from the bank, tipped sideways, and slid down into the channel with a wet, heavy, final sound. They had been measuring this exact thing for years, creek banks peeling backwards by 1/3 of a meter, sometimes more, every single year. One of the most important coastal wetlands on the entire western seaboard of the United States was coming apart at the seams, edge by edge, like a jumper unraveling from one pulled thread. And every model the scientists had built told the same grim story. Faster erosion, more collapse, a marsh sliding inevitably towards open mud, and then open water. But that is not what happened. Because in certain stretches of that same estuary, the banks had simply stopped retreating. They had gone firm. They were holding. And when the researchers looked closely at what was different about those particular stretches, the answer was not a seawall. It was not a single sandbag or a sheet of engineered steel. The thing quietly stitching that marsh back together was an animal. A small, whiskery, almost comically charming animal, floating on its back in the channels, cracking open crabs on its chest. I'm Edmund Hale, and this is the story of how a creature we very nearly wiped off the face of the Pacific came back into a dying Californian estuary that nobody had asked it to repair, and began undoing damage that engineers, agencies, and a great deal of money had never managed to touch. How a salt marsh that had been collapsing for the better part of a century stopped collapsing. And the genuinely surprising, peer-reviewed science of how a sea otter, of all the animals on Earth, turned out to be one of the most effective coastal engineers anyone has ever put a number on. But before we get to the otters, you have to understand the place. And you have to understand what was killing it. The estuary is called Elkhorn Slough. It sits on the central coast of California, about halfway up the long sweep of Monterey Bay, just inland from a small working harbor at a place called Moss Landing. If the word slough is unfamiliar, picture a slow tidal waterway, a winding arm of the sea that breathes salt water in and out twice a day through a maze of muddy channels and low green marsh. Elkhorn is one of the largest tracts of tidal salt marsh left anywhere in California, second only to San Francisco Bay itself. And like almost every salt marsh on Earth, for most of its history it was treated as more or less worthless. Because a salt marsh does not look like much. It is not a coral reef. It is not a redwood forest. It is a flat, muddy, green and brown plain of waving cordgrass and fleshy pickleweed, smelling of salt and warm mud, threaded through with twisting little creeks. For centuries, people drained marshes, diked them, filled them in, and built on top of them. Because to the untrained eye, a salt marsh looks like wasted, half-finished ground, neither honest sea nor honest field. And that impression is one of the most expensive mistakes in the history of how we value land. Because acre for acre, a healthy salt marsh is one of the most quietly valuable ecosystems anywhere on the planet. It is a nursery where huge numbers of fish and crabs and shellfish spend the most vulnerable weeks of their lives sheltered among the protective grass. It is a shock absorber, soaking up storm surges and high tides that would otherwise hammer the coast behind it. It is a water filter, stripping pollutants out of the runoff before they ever reach the open sea. And it is a carbon vault. Salt marshes lock carbon away in their deep, waterlogged, airless mud at a rate that puts most forests to shame, and they hold onto it for centuries. So when a marsh like Elkhorn unravels, you are not just losing scenery. You are losing a machine that does an enormous amount of unpaid work for everything and everyone around it. And Elkhorn had been losing that machine for a very long time. The slide began back in the 1800s, when settlers diked and drained the marsh for pasture and crops and salt ponds, cutting great sections of wetland off from the tides that kept them alive. But the single heaviest blow landed in 1946. Engineers cut a new, permanent mouth through the sand barrier to make a reliable harbor entrance at Moss Landing. And in doing so, they opened the slough directly to the full muscle of Monterey Bay. Almost overnight, the tides surging in and out of those narrow, winding channels became far more powerful than anything the marsh had ever evolved to cope with. The rushing water carved the channels deeper and wider. The banks began to bleed away. By the time researchers were carefully counting in the early 2000s, Elkhorn Slough had lost roughly half of its tidal salt marsh since the 1870s, and the loss was still going, year after year. And there was a second killer, a quieter one, and this one came down off the land. The valleys draining into Elkhorn include some of the most intensively farmed countryside in the United States, the vegetable fields of the Salinas Valley, a region that proudly calls itself the salad bowl of the world. All that farmland sheds fertilizer. Nitrogen and phosphorus run off the fields, down the creeks, and into the slough. And in a wetland, a flood of fertilizer is not a gift. It is a slow poison. It throws the whole system out of balance, feeding explosions of algae and reshaping the food web from the bottom up. And, as we are about to see, it did something specific and destructive that almost nobody fully understood until very recently. It helped to unleash a crab. To see how, you have to look at what actually holds a marsh bank together. The green skin of an Elkhorn Creek bank is Pacific cordgrass, a tough, salt-tolerant plant whose real work happens underground. Beneath the surface, cordgrass sends down a dense, fibrous mat of roots that binds the soft mud into something solid, a living net of root and soil strong enough to resist the daily pull of the tide. As long as that root mat is intact and healthy, the bank holds. Pull the roots out, and the bank is just wet mud waiting to slump. And living in those banks is a small, common, unremarkable-looking creature called the striped shore crab. On its own, in modest numbers, it does no real harm. It digs its burrows in the bank and nibbles at the cordgrass, and the marsh shrugs it off. But when the crabs are not kept in check, their numbers can climb, and a dense population of them becomes a wrecking crew. They honeycomb the banks with their burrows, riddling the mud with holes. And they graze the cordgrass hard, chewing the stems and the roots, thinning out the very root mat that holds everything together. A bank that has been hollowed out by burrows and stripped of its binding roots has no strength left in it. The next strong tide simply peels it away. Now add the fertilizer back into the picture. The nutrient pollution pouring off the farmland supercharges the lower end of the food web, and the result is more food and more crabs in a marsh that had already lost most of the predators that used to keep them down. You end up with a bank under attack from below by an animal nobody was even watching, in numbers the system was never built to carry. That, in plain terms, was the machine quietly tearing Elkhorn Slough apart. And the thing that turned it off was the return of a predator. Now, the sea otter. And the first thing to say is that the animal is far stranger and far more formidable than its reputation suggests. Yes, it is the creature you have seen floating on its back, paws tucked up, looking like the single most charming thing the ocean has ever produced. But underneath that, a sea otter is a relentless, ravenous marine predator with one of the most extreme lifestyles of any mammal alive. Unlike seals and whales, the sea otter has no blubber, no thick layer of fat to keep it warm in cold Pacific water. Instead, it relies entirely on its fur, and that fur is unlike anything else in nature, packed at a density of up to 1 million hairs in a single square inch. It is the thickest coat of any animal on Earth, a coat so fine it traps a permanent layer of air against the skin. But a coat is not enough on its own. To stay warm in that cold water, an otter has to burn fuel at a furious rate, which means it has to eat and eat and eat. A sea otter gets through around a quarter of its entire body weight in food every single day. Imagine eating 20 or 25 kilograms of seafood a day, every day, for life. And a great deal of what it eats is exactly the kind of thing that was tearing the marsh apart. Crabs, including, as it turns out, the striped shore crabs burrowing into the banks of Elkhorn Slough. This is what ecologists mean when they call the sea otter a keystone species. And the otter is, in fact, the animal that gave us the very idea. Back in the 1970s, a young scientist named Jim Estes went out to the cold waters of the Aleutian Islands off Alaska to study them. And he stumbled onto something that reshaped the whole of modern ecology. Where the otters were present, the seafloor was carpeted in towering underwater forests of kelp, alive with fish and life. Where the otters were absent, that same seafloor was a barren, lifeless desert of bare rock. The difference was the otters, and the link was an animal in between, the sea urchin. Urchins eat kelp. When otters are around, they eat the urchins and keep them down, and the kelp forest flourishes. Remove the otters, and the urchins explode and mow the kelp forest to stubble. One predator at the top, controlling the whole system beneath it. That is a keystone species, the single stone that holds the entire arch in place. And what was about to happen in a muddy Californian estuary was that exact principle. The otter and the urchin and the kelp playing out again in a completely different setting, with crabs and cordgrass standing in for urchins and kelp. But for that to happen at all, the otters first had to come back from the brink of total annihilation, because we very nearly lost them forever. The sea otter has the densest, most luxurious fur of any animal on the planet, and that beauty very nearly killed the species outright. From the 1700s into the 1800s, the maritime fur trade swept up and down the Pacific coast of North America, from Russia and Alaska all the way down to California, and hunters slaughtered sea otters by the hundreds of thousands for their pelts. It was one of the most intense commercial hunts in history, and it was brutally efficient. By the early 20th century, a species that had once numbered in the hundreds of thousands, ranging across the entire northern Pacific Rim, had been all but exterminated. The southern sea otter, the subspecies that belongs to California, was simply assumed to be gone, extinct. For decades, nobody expected to see one again. And then, in 1938, with the opening of a new stretch of coastal highway along the wild cliffs of Big Sur, a small group of people looked down into a hidden cove and saw them. A tiny remnant population, perhaps only around 50 animals, had clung on in that remote, almost unreachable corner of the coast, out of sight for a generation. Every southern sea otter alive in California today descends from that single handful of survivors. The species had threaded the eye of a needle, and slowly, under legal protection, it began to spread back along the coast. It took the better part of a century for that recovery to reach Elkhorn Slough. Otters began appearing in the estuary in real numbers only in the last few decades, drifting in from the open coast and discovering, to their evident delight, a sheltered, food-rich wetland packed with crabs and clams. And they did not just visit, they moved in, settled, and bred. The slough turned out to be close to perfect otter habitat, and the population there grew into one of the densest concentrations of sea otters anywhere in California. Around 100 animals making their entire living in this one small, winding estuary. For the marsh, it meant that for the first time in roughly 100 years, a serious crab-eating predator was back in the system, in force. And that set up one of the most revealing natural experiments in the whole of modern conservation science, The person who pieced it together is a marine ecologist named Brent Hughes of Sonoma State University, who had been working in Elkhorn Slough for years. And what Hughes and his colleagues realized was that the otters had, without meaning to, handed them a perfect study. Because the otters had not recolonized the whole estuary evenly, or all at once. There were stretches of marsh with lots of otters, and stretches with very few. And there were decades of records, aerial photographs going back to the 1930s, careful measurements of how fast the creek banks were eroding, so they could line it all up and ask one simple question. Did the arrival of the otters actually change what was happening to the marsh? And they did not just rely on watching either. They ran the experiment directly, fencing off sections of bank to keep crabs out and comparing what happened where otters were present against where they were not. They counted crabs, they measured cordgrass, and they tracked the banks themselves, foot by foot, over years. And the results, published in the journal Nature in early 2024, were striking. Where the otters had returned in strength, the crab populations were dramatically lower, in places only a fraction of what they were in the otter poor stretches. With the crabs held down, the cordgrass recovered. Its root mat thickened and spread and gripped the mud again. And the banks, the same banks that had been peeling away for decades, stopped peeling. In the stretches with the most otters, the team found the creek banks were eroding far more slowly than in the stretches without them, by as much as 80 to 90%. Let me put that another way. The otters, simply by being otters, by floating around eating crabs all day to fuel that ravenous metabolism, had slowed the collapse of the marsh edge to a crawl. They were doing, for free, the work that no seawall and no restoration budget had ever managed to do. And the researchers were careful and honest about what this did and did not mean. The otters had not reversed the damage. They had not rebuilt the marsh that diking and tidal scour had already destroyed. What they had done was halt the bleeding at the edges, stabilize what was left, and buy the whole system something it had been running out of: time. And there is a deeper idea buried in that result, one I think is genuinely important. Remember the two forces that were killing Elkhorn. There was the brute physical force of the scouring tides, and there was the chemical force of all that fertilizer pouring off the farmland, feeding the crabs from the bottom of the food web upwards. Those are what ecologists call bottom-up pressures, problems pushing up from the base of the system. Nobody had switched off the fertilizer. The Salinas Valley is still farming, the nutrients are still flowing. And yet the marsh stabilized anyway, because the otters applied pressure from the very top of the food web downwards. And that top-down force turned out to be strong enough to counteract a bottom-up problem we have struggled for decades to fix any other way. A predator at the top of the chain was compensating for pollution at the bottom of it. That is a profound and slightly humbling thing to discover, because it suggests that in a damaged ecosystem, putting the right predator back can sometimes do work we assumed could only be done by cleaning up the source. Not always, not everywhere, but sometimes. And at Elkhorn, measurably. Now, I want to be careful here, because the version of this story that just says, "Otter's good, problem solved," is not the honest one. And the honest one is more interesting. The first complication is that sea otters do not only eat the crabs we are happy to see them eat. They eat everything, including Dungeness crab, clams, abalone, urchins, the very shellfish that commercial fishermen and divers depend on for their livelihoods. The same appetite that heals the marsh puts the otter squarely into conflict with people up and down the California coast. And that conflict is real, and it is not going away. Where otters expand, certain fisheries shrink, and the people affected are not villains for noticing. The second complication is scale. Elkhorn Slough is one small estuary, and it happens to be close to perfect otter habitat, sheltered, calm, and full of food. Most of the open coast is not like that, and you cannot simply sprinkle otters across every degraded wetland and expect the same result. The third complication is the one looming over all coastal marshes everywhere, and that is sea level rise. An otter can hold a creek bank against the crabs. It cannot hold a marsh against a rising ocean. And the fourth is that the underlying wound, the nutrient pollution, is still untreated. The otters are compensating for it, not curing it, and a compensation is only ever as reliable as the animal providing it. So this is not a tidy victory. It is a powerful, real, carefully measured piece of good news, with hard edges and clear limits, which is exactly the kind of conservation story I think is worth telling honestly. But step back and look at the whole shape of it, because it really is remarkable. For close to 100 years, the channels of Elkhorn Slough held the memory of an animal that no living person along that coast had ever seen swimming there. The marsh had evolved over thousands of years with otters in it, shaped by their hunger, kept in balance by their appetite. And then, for a century, that piece was simply missing, and the system slowly came undone in ways nobody could quite explain or stop. And then the otter came home. Not because we engineered it back into that exact role, not because anyone planned for it to save the marsh, but because we finally stopped killing it and gave it room and time. And it found its own way back into the slough and started doing, instinctively, the job it had always done. The crabs went down. The cordgrass came back. The banks held. An estuary that had been quietly falling apart for a century steadied itself, held in place by an animal floating on its back, cracking open a crab in the afternoon sun, with absolutely no idea that it was performing one of the most cost-effective acts of coastal engineering anyone has ever measured. And that, I think, is the lesson that reaches well beyond one muddy estuary in California. We tend to assume that repairing a broken ecosystem is a matter of more engineering, more concrete, more control, more clever human intervention. Elkhorn suggests something humbler and stranger. That sometimes the most powerful tool we have is a predator we nearly destroyed, returned to a place that has been missing it, and then left alone to do what it evolved to do. We did not save that marsh with a machine. We saved it by getting an animal out of the history books and back into the water, and then having the sense to step out of its way. If this story moved you the way it moved me, let me know in the comments, and tell me whether you think we should be doing far more to bring sea otters back to the coastlines they used to hold, even where it means hard conversations with the people who fish those waters. If it changed the way you think about what these animals actually are, beyond the cute floating image, share it with someone who would appreciate it. And subscribe, because there are more of these comeback stories than you would ever believe, and I have got plenty more to tell you. I'm Edmund Hale. Thanks for watching.